In section 11.3, I'm going to go over how to perform operations with complex numbers. And remember, complex numbers are numbers that are in the form a plus bi, where a and b could be any real numbers at all. So we're going to go over how to add, subtract, multiply, and divide those kinds of numbers. And I'll start with addition and subtraction. Now I'll start out with an addition example, because that's extremely simple. To add two complex numbers, all we want to do is combine the like terms. So the parts that are just regular whole numbers or real numbers, like the 15 and the 6, can be combined. So 15 plus 6 would be 21. And then the two imaginary parts can be combined. So you have a negative 2i and a positive 17i, which would be plus 15i. So it's really just like combining like terms. The two numbers are the like terms, and the two terms that have i's in them are considered like terms, and you can just combine the like terms. Now let's do subtraction. Now subtraction is a little bit trickier because, again, we are going to want to just combine the like terms, but first we have to really make sure we take proper care of dealing with this minus sign that's coming in front of that second set of parentheses. Really what we have there is we have an implied 1, and in fact it's an implied negative 1 that has to get distributed through that second set of parentheses. So we'll do that first, and then we'll combine the like terms. So in this case, we'd have 9 minus 4i, and then we have negative 1 times 8, so minus 8, and then a negative 1 times a negative 2i, which is plus 2i. And now that we've done that, we can just combine the like terms. So 9 minus 8 would just be 1, and negative 4i plus 2i would be negative 2i. So the answer would be 1 minus 2i. Now in this next example, the numbers that we're dealing with aren't already in I form. So you've got a couple of imaginary numbers here. You've got the square root of negative 1. That's really I. And you've got the square root of negative 64. Now the square root of 64 would be 8, but since it's a negative 64, that means it's 8i, because it's an imaginary number. So you'd always want to convert them over to I form first. So really what we have here is 3 minus I minus 3 plus 8i. Now again, we have to make sure we deal with the subtraction correctly. We're going to distribute the negative 1 through the second set of parentheses first. And that would give us 3 minus I minus 3 minus 8i. And then after we distribute the negative 1, then we can just combine the like terms. So we have 3 minus 3 is just 0. And then negative I and minus ai would be negative 9i. And so that would be our answer. Next, I'd like to go over how to multiply complex numbers. Now, when we multiply complex numbers, we use a lot of the same laws that we do in regular algebra, like when we multiply polynomials. But after we've done that, we have to remember that when we're dealing with I squared equals negative 1. And the reason that's true is because since I is the square root of negative 1, by definition, I squared would have to equal negative 1. So after we do the multiplication, we'll always want to replace any I squareds with negative 1 and then simplify it down even further. So let me give you some examples. Let's say we had negative 7i times 4i. Now you can kind of treat this just like it was algebra, like I was a variable. Like if pretend it was negative 7x times 4x. You could do that. So you do this the same way. And when you do that, you get negative 28 I squared, because you have an I times another I. But then, the I squared, you need to replace that with negative 1, as I said before. So this is really negative 28 times negative 1. And so it's a negative times a negative, so it's actually a positive 28. And that would be your final simplified answer. All right, let's take another example. Let's say we had the square root of negative 49 times the square root of negative 16. Now you're going to want to write these in terms of I first. These are both imaginary numbers. This first one could be changed into 7i because the square root of 49 is 7. And since there's a negative number underneath the square root, that makes it an imaginary number, so 7i. And similarly, the second imaginary number can be turned into a 4i. So make sure to do that step first. Write them in terms of I if they're not already. And then, from there, you would do it out the same way. So you'd have 28i squared, which would be 28 times negative 1. So this time it's going to come out to be negative 28. In this next example, we're going to have to use the distributive property. We're going to take the 6i and multiply by both terms inside the parentheses. So 6i times 1 would of course just be 6i. And then 6i times 3i would be 18i squared. So plus 18i squared. Remember, anytime we have I squared, we change it into negative 1. So that's going to be 6i plus 18 times negative 1, which is really 6i minus 18. Or a lot of times we want to write them in the form a plus bi, so we'll write the negative 18 first and then plus 6i. And you can see that's now in the form a plus bi, and it shows it's a complex number. Okay, in this next example we have two complex numbers being multiplied together, 7 plus 3i times 10 plus 2i. Now if this was algebra, you'd probably think to use the FOIL process, where you do your first, outers, inners, and last. And that is what we're going to do here. So we'll do 7 times 10, that's 70. And then our outers, so 14i, so plus 14i. And then the inners, so plus 30i. And then the lasts, so plus 6i squared. And usually when we do FOIL, we can combine the inners and outers together, so we go ahead and do that. So that would be 44i. But now also here, remember this I squared right here, we want to replace that with negative 1. So that's plus 6 times negative 1, which is really minus 6. So we have 70 minus 6. Those end up being like terms as well. So what's 70 minus 6? Well, we'd have 64 plus 44i for our final answer. Okay, let's try another example similar to this. We have 8 plus 3i times 8 minus 3i. This would still be a FOIL problem. This is actually a special kind of FOIL problem because we have two what are called complex conjugates, meaning they're the exact same expression except in one case there's a plus and in one case there's a minus. So those are called conjugates. Anything of the form a plus b and a minus b are called conjugates, and these, since they're complex numbers, are called complex conjugates. At any rate, when we do the FOIL on that, we get 8 times 8 is 64. And for the outers, we have negative 24i. And for the inners, we have a positive 24i. Notice the inners and outers cancel, which always happens when you multiply conjugates together. And then you have a minus 9i squared. Now minus 9i squared is really plus 9, because remember I squared equals negative 1. So really what we have here is 64 minus 9 times negative 1, which is the same as 64 plus 9, which would be 73. Notice in this case, our answer doesn't have any I in it at all. And that's because the only place where the I's appear in a FOIL problem is in the inners and outers. And the inners and outers always cancel when you multiply conjugates together, which means you'll end up with a real number for your answer. That ends up being important when we get to division in just a minute. Now let's say we have a complex number like 7 minus 4i that's squared. Well, the important thing to remember when you square any binomial, meaning something with two terms, is you have to take the entire thing, 7 minus 4i, and multiply it by itself by another 7 minus 4i. And so that becomes a FOIL problem, even though it might not look like one at the beginning. So that's the critical step. And then once you do that, you do your firsts, which would be 7 times 7 is 49, and then you do your outers, so you'd have minus 28i, and then you do your inners, that's another minus 28i, and then you do your lasts, which would be positive 16i squared. And then we just simplify, so we have 49. If we combine these like terms together, we have minus 56i, and then in this last case, since I squared is negative 1, that's really 16 times negative 1, so it's really minus 16. So that equals 33 minus 56i. And that'd be your final answer. So the last operation to go over is division, and dividing complex numbers is definitely the trickiest of the operations to do. In order to divide complex numbers, we have to multiply both the numerator and denominator by the conjugate of the denominator. Now that's a mouthful, so I'll go ahead and write that down. So let's say we were dividing 4 by 4 plus 3i. So we'd have to take the denominator, 4 plus 3i, okay, and take the conjugate of that just means change the plus to a minus, and multiply the top and the bottom both by 4 minus 3i. So we'd set it up like this. We're going to say times 4 minus 3i here, and 4 minus 3i in the bottom. So we're multiplying the top and the bottom by the same thing. So it's going to give us an equivalent fraction. And when we actually do these multiplications, we have to keep in mind that we'll have to use the distributive property. So there's really a set of parentheses here, so this 4 is going to get distributed. And in the bottom one, you actually are going to have to do FOIL, because you have two binomials. So that's going to give us, let's see, 4 times 4, that's 16 minus 12i in the numerator. And then in the denominator, we'll do the FOIL. So 4 times 4 is 16. And then you have a minus 12i for the outers and a plus 12i for the inners. And notice they're going to cancel, which is the reason we're doing this. And then we have minus 9i squared. And so that will give us 16 minus 12i divided by 16 minus 9 times negative 1, which is 16 minus 12i over 16 plus 9. And 16 plus 9 is 25. So you have 16 minus 12i over 25. And sometimes we'll leave our answer like that. But you can also break that up into two separate fractions and do 16 over 25 minus 12 over 25 times I. And the only advantage to breaking it up and writing it like that is because now you can see it's in the form a plus bi. So it's another complex number. When it's in this form, it doesn't quite look like a plus bi, but over here it does. So sometimes we'll expand all the way out to this point. Let's say we have 5 plus 8i divided by 3 plus I. So again, we want to find the conjugate of the denominator, which would be 3 minus I. That plus gets changed into a minus. And if it was a minus to start with, we'd change it into a plus. So we're going to multiply both the top and the bottom of this fraction by 3 minus I. Now in this case, we really have two FOIL problems to do. So we'll go ahead and do that. So in the numerator, I'm going to do the first, the outers, the inners, and the last. So 5 times 3 is 15. 5 times negative I is negative 5i. 8i times 3 is 24i, so plus 24i. And then 8i times negative I is negative 8i squared. Now I know I can simplify that, but I'm just going to write it that way for now, and I'll simplify it in the next step. In the denominator, we have 3 times 3 is 9, and then minus 3i for the outers, and plus 3i for the inners, and then minus I squared for the lasts. So let's now just combine our like terms. So in the numerator, a negative 5 plus 24 is 19 plus 19i. And minus 8i squared. Remember, I squared is negative 1. So that part right there is really minus 8 times negative 1, which will be plus 8. So I'm just going to write that down as plus 8 here. And then in the denominator, the inners and outers cancel, as they always will because they're conjugates. And this is going to be minus a negative 1, which will be plus 1. So we get 9 plus 1. And then you just want to combine your constants together, your like terms. So 15 and 8 is 23. So 23 plus 19i over 10. And then again, we can split that up into two separate fractions and say 23 over 10 plus 19 over 10 times I. Now in this last division problem, it's kind of an exception to the rule. We have 2 plus 8i over 3i. Now generally, as I said before, you're going to want to multiply the top and the bottom by the conjugate of the denominator. But in this case, when your denominator is just an imaginary number, so it's just a number times I, or a bi, with no a in it, you can do it a little bit more easily. In that case, when you just have a bi in your denominator, and that's all, the easiest way to divide it is to multiply the top and the bottom just by I. Okay? Now, the conjugate would actually be, this complex number is really 0 plus 3i. So the conjugate would really be 0 minus 3i, which would be negative 3i. But you don't really have to multiply by that in this case. It's kind of the exception. It will work. You can do it that way, but this is a little shorter. So if you multiply by the I, again, you have to distribute that in the top. That would give you 2i plus 8i squared over 3i squared. And remember, I squared equals negative 1, so that's 2i plus 8 times negative 1 over 3 times negative 1, which would be 2i minus 8 divided by negative 3. Which, if I want to write that as a complex number, I could split this up and write it as 2 over negative 3i plus a negative 8 over a negative 3. Now the negative divided by a negative is a positive, so I could say 8/3 minus 2/3 I. And that would really be the best answer.